Lesson 8.1.2, Exploring the Sampling Distribution of Differences in Two Proportions. Introduction. According to a Gallup report from March 2016 entitled U.S. Concern About Global Warming at 8-Year High, concern about the impact of climate change among U.S. adults has returned to the level of its previous peak in 2007. Additionally, the results of the Gallup survey suggest we may be seeing the highest ever proportion of U.S. adults who believe humans are the cause of climate change. Of the 1,019 randomly selected participants, 65% chose the effects of pollution from human activities over natural changes in the environment as the explanation for changes we are seeing in the climate. Previously, this belief was highest in 2007, when 61% of U.S. adults in a similar Gallup poll cited human activities as the cause of climate change, n equal to 1,012 for that one. Even though the sample proportions were different in 2007 and 2016, the difference in the sample proportions could be due to sampling variability rather than differing underlying population proportions. Try these. Researchers wanted to understand the sampling variability that can occur when we measure sample proportions. They used computer software to simulate the samples for the two different years of study, 2007 and 2016. For both years, the researchers used samples of size 25 and computed the sample proportions of adults who believe that human activities explain the changes we are seeing in the climate. These two collections of sample proportions are plotted together on a dot plot we will see below. The population proportion for 2007 was assumed to be 0.61. The population proportion for 2016 was assumed to be 0.65. In this activity, P1 equals 0.61 will represent the population proportion for 2007, and P2 equals 0.65 will represent the population proportion for 2016, and P1 hat and P2 hat represent the sample proportion simulated for 2007 and 2016 respectively. The corresponding population proportions are P1 and P2. Okay, so P1 represents the earlier year, 2007, and P2 represents the later year for 2016. Think about the criteria for approximate normality. N times P is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10. Would the sampling distribution of sample proportions for both years satisfy the conditions for approximate normality? Fill in the table below to help you answer this question. Okay, so what are the sample sizes? If we read back here, it did say that we are using samples of size 25 for this problem. Okay, so we're going to put 25 for both of these. Now for N times P, it's going to be 25 times something. Let's see. What was my P1? My P1 was 0.61. My P2 was 0.65. So this is 0.61. So this would be 25 times 1 minus 0.61. So if I multiply this on my calculator, I get 15.25. And if I do 25 times 1 minus 0.61, I get 9.75. Now let's try this one. If I do, let's see, my second sample size was, my second proportion was 0.65. So if I multiply these, 25 times 0.65, I get 16.25. And this one is 25 times 1 minus 0.65. I get 8.75. So no conditions are met. Actually, no for both of these because these numbers are both smaller than 10, right? Everything needs to be bigger than 10 in order for normality to hold. So unfortunately, a sample size of 25 is just not big enough. So going on, the researchers decided to increase the sample size to n equals 100 for both years. Let's see if this makes a difference. 100 times 0.61 is actually 61. And 100 times 1 minus 0.61 is 39. 100 times 0.65 is 65. And 100 times 1 minus 0.65 is 35. So in this case, the answer is yes for all of these, right? Because everything is bigger than 10, so we're good. So we're going to go with a size of 100. Below are two dot plots showing sampling distributions for 2007 and 2016. Each displays 100 samples, and each sample assumes a sample size of 100. So don't let this confuse you. For the top one in 2007, what they did was they took a sample of 100 people, they calculated the proportion of them that believe in global warming, and that's just one dot, and then they repeated that experiment 100 times. The bottom one is the same thing except it was in 2016. So overall, we're talking about 200 samples here, right? Okay. So look at the distributions of sample proportions for 2007 and 2016. Do they appear to be sampled from approximately normal sampling distributions? To me, this looks pretty normal, right? If I were to draw this in, that looks kind of normal. And that looks kind of normal too. So I would say yes, they are roughly, yes, they look roughly normal. They don't look perfectly normal, but we don't expect them to look exactly. How are the distributions of sample proportions different for the 2 years? Well, I mean, let's look at these pictures. How do they look different? To me, just looking at this roughly, let's talk about their center and let's talk about their spread as well. So I would say that their spreads look about the same. However, the center for this picture seems to be about right here, and the center for this other picture seems to be a little to the left, right? So I would say the mean for (2016) is slightly bigger than the mean for 2007. But I will say the standard errors look about the same. Okay, because both pictures look about the same amount spread out. Is it possible to select two sample proportions, one from each year, that lead you to conclude that the proportion of people who feel human activities are the cause of climate change decreased from 2007 and 2016? If so, explain. So, yes, I would say it is possible because, look, what happens if in 2007 you look at a sample and you get something, let's say this guy, you get one that's a little high, and then the next time you do a sample in 2016, you get one that's on the lower side. It's easy to conclude that it's gotten smaller, hasn't it? Even though overall that doesn't seem to be the trend here. Okay, so yes, it is possible since there are some dots on the 2007 sample distribution that are larger than some dots on the bottom. Okay, so this is not good, right? There are some misleading samples that can be taken. Next, is it possible to select two sample proportions, one from each year, that lead you to conclude that the proportion of people concerned about the effects of global warming has increased? If so, explain. Well, by the same reason, this time let me use blue, right? It is certainly possible that we can find, let's see, where is it? It is certainly possible that we can find a dot on the left that is smaller than a dot on the top that is smaller than a dot on the bottom. So I'll say yes, since some dots on the top are smaller than some dots on the bottom. Think about how the samples are distributed. Why might you see conflicting conclusions occurring? So when we look at pictures like this, what's the problem of telling that one is definitely bigger than the other? Why is that not the case? And the case is because there's simply too much overlap in these pictures, right? In fact, if there's any overlap at all, then that means it is possible to get two things that are the same, which means that it's hard to tell which one's bigger, right? So let's say we can see some possible conflicts because the two charts overlap in large chunks, right? I would say they have a great deal in common. How could we minimize the overlap between the sampling distributions? Well, I want you to recall how we reduce the standard error, right? Remember, increasing the sample size always accomplishes this. If we increase the sample size, what's going to happen is the two pictures will get skinnier and skinnier, and it'll be possible for us to make them not overlap at all. So we could reduce the overlap by increasing both sample sizes. Okay. Let's move on. Researchers were interested in understanding the variability in the differences in sample proportions. Using the simulated proportions from 2007, that's P1 hat, and the simulated proportions for 2016, P2 hat, they computed 1,000 randomly matched differences, P1 hat minus P2 hat, between the proportions. The differences were plotted on the following dot plot. Okay, so this is a new thing that we can get by taking essentially dots on the top picture and subtracting dots on the bottom picture. Recall that in this simulation, P1 is assumed to be 0.61 and P2 is assumed to be 0.65. Locate the difference between these proportions on the dot plot above. Okay, so if we do 0.61 minus 0.65, we end up with negative 0.04. So where does that live in our picture? Let me use red here. Negative 0.04 is right here. Negative 0.04. Okay, so let's look at part B. Actually, before we do part B, let me go ahead and give you guys the code word for this lesson. It is climate. Okay, the code word for this lesson is climate. Okay, let's move on. Describe the distribution of differences, P1 hat minus P2 hat, in terms of shape and center. Well, this looks pretty normal to me. I'm hoping you guys agree. This is pretty normal. And shape is bell-shaped. Or another word for that is normal. And the center is about negative 0.04, right? Would you guys agree with that? That number looks like it's pretty much in the middle of this. Let's move on. In a previous lesson, we learned about the standard error formula for the sampling distribution of P1 hat minus P2 hat. Use the values for P1 and P2 to determine the standard error where N1 and N2 are both 100. So what are we going to put in our calculator here? So P1, remember P1 is 0.61, so it's going to be 0.61 times 1 minus 0.61 divided by 100 plus 0.65 times 1 minus 0.65 divided by 100. And remember, all of this should be under the square root. So I'm going to cut to the calculator so we could see this being calculated. So coming over to the calculator, we're going to hit second square root, and then I have 0.61 times 1 minus 0.61, close parentheses, divided by 100, plus 0.65 times 1 minus 0.65, close parentheses, divided by 100 again. If we hit enter on that, we end up with 0.068. 0.068. So here we got 0.068. Okay? So this would be the standard error for our new distribution, right, for the differences. Okay? It is often important to assess whether a specific difference in sample proportions is unusual. Use the mean and standard error of the differences in sample proportions to determine whether or not the difference of P1 hat minus P2 hat equals 0 is unusual. Okay. So how would we figure out whether that is unusual or not? We want to see how many standard deviations 0 is from the mean, right? Well, do we need to do that? I think they want us to do that for the next part, right? So let's just think about this. If we come over here, right, the mean is negative 0.04. We're trying to figure out if this 0 is unusual. It doesn't look unusual to me, right? It's pretty close to the mean in our picture. Okay? Say, so if the mean is negative 0.04, right? This is the mean. What is the mean plus 1 standard deviation? The mean plus 1 standard deviation, so we're going to take negative 0.04 and we're going to add a standard deviation which we got in this last problem to be 0.068. So what happens when you add a negative and a positive? You can use your calculator, you get 0.028. Okay? What does that mean? I can stop right there. This means 0.02 is somewhere around there, which means that 0 is closer than 1 standard deviation. So it is definitely not unusual, right? So let's get that down here. 0 is closer than 1 standard deviation. So it is not unusual. Part E. We can use the normal distribution to determine the probability of observing a difference in sample proportions of 0 or less. Find the z-score for a difference of 0 using the mean and standard error of the differences in sample proportions. And remember that the formula for the z-score is the following. Now, this might look really confusing to you. We've never seen this formula before, right? But remember, what we were doing before is p hat minus p divided by sigma, right? We're doing the exact same thing here, except the only difference is instead of p hat, we're doing a difference, right? So instead of p hat, we're doing p1 hat minus p2 hat, and instead of p, we're doing p1 minus p2, and then remember that bottom square root has gotten more complicated also. Okay, so let's see what we get. Remember, we're assuming a difference of 0, right? In other words, we're assuming that this whole thing is 0. So we get 0 minus negative 0.04. Why do we get that? Because remember, P1 minus P2, we did that right up here. P1 minus P2 is negative 0.04, right? Okay. Divided by, we already did this bottom division. We did it, or sorry, the square root, right? It's 0.068. So what do we get for the z-score? We need to put that in our calculator. Okay, so I'm going to put this in my calculator and I'm going to be really careful about using parentheses. First, I'm going to open the parentheses to use the top fraction. So it's going to be open parentheses, 0 minus, and then parentheses again for the negative number. Now be careful, the negative number, you do not press this minus sign, you push the little negative symbol here. So it's negative 0.04. Close parentheses, close parentheses. Now we're saying we're done with the top number, so we're going to divide it by 0.068. When we hit enter, we get 0.59 if we round it to 2 decimal places. So we get equals 0.59. Okay, that's our z-score, right? And that makes sense because this is less than 1 standard deviation away, isn't it, right? That's what a z-score is. It's the number of standard deviations. Okay, so let's keep going. Suppose we have 2 random samples, one from each year. What is the probability that the difference in sample proportions would be greater than 0? Okay, well, we're talking about our normal curve. 0 is somewhere around here, and what we're talking about then is wanting to know what this area is, right? So how are we going to do this? Remember, we have normal CDF, right? We're going to do normal CDF, and sorry, this should say 0.59 because we want to convert it to z-scores, right? And so that's what we did just above in this problem. So we're going to do normal CDF, and the left limit is going to be 0.59, and then the upper limit is going to be 1E99. So I'm going to put that in my calculator. Let's see what we get. So coming over to the calculator, remember we want to do second DISTR, go down to normal CDF, hit enter. I have 0.59 and the 1E99 I'm going to leave alone. Paste and then enter again. This gives me 0.278. Let's go to 278. So we get 0.278. Okay, that's not that unlikely, right? 0.278 is not very unlikely. Okay, so let's keep going. We would like to increase the likelihood that the difference in the randomly selected sample proportions is close to the actual difference in population proportions. What could we do to make it more likely? So the way that we would do that is we would want to make our sample proportions close to the mean, and the way we can make it close to the mean is by having a smaller standard error. And the only way we could decrease our standard error is increasing the sample sizes. So let's write that down. If we increase the sample sizes, this would decrease the standard error of the sampling, standard errors of the sampling distributions. So P1 hat and P2 hat would be closer to P1 and P2. Okay? All right. And let's go to number 4. Suppose we use the actual sample sizes from the Gallup studies. Let N1 equal 1012 for 2007 and N2 equal 1019 for 2016. Will a change in sample sizes affect the mean of the sampling distribution of the differences? And what is the mean? So they're trying to trick us here, right? We know that the mean never changes with this stuff, right? The mean of a sampling distribution is always just equal to the population proportion. So no, the mean of P1 hat minus P2 hat is P1 minus P2 regardless of sample size. What is the mean of the sampling distribution? We already know what the mean is, right? Isn't the mean is negative 0.04? Are the conditions for normality still satisfied? The answer is yes, because the sample sizes are even bigger. Are even bigger now, so all expected successes and failures is larger than 10. I mean, you could multiply it out, but we don't really need to, right? If you increase your sample size, of course, it's still going to be normal, right? Use the new sample sizes to determine the standard error of the sampling distribution of the differences. What happened to the standard error when we increase the sample sizes? Well, let's see, right? Remember our standard error formula, right? We have the square root of, remember it's P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. So that's going to be 0.61 times 1 minus 0.61 divided by, let's see, what did we make our sample size? 1012 plus, then we have 0.65 times 1 minus 0.65 divided by 1019. Okay. So let's go ahead and put this in our calculator and see what we get. Okay, so we're going to put that guy in our calculator. Remember, we need to put second square root first. And then I have 0.61 times 1 minus 0.61, close parenthesis, divided by 1012 plus 0.65 times 1 minus 0.65, close parentheses, divided by 1019. So when we put that in our calculator, we end up with a much smaller standard error, don't we? 0.021. So I get 0.021. Let's go ahead and find the z-score. Recall that the z-score is equal to P1 hat minus P2 hat minus P1 minus P2 divided by that big square root that we have right here. Okay? So what do we get? Well, remember, P1 hat minus P2 hat, what we're talking about is the number 0. That's what they're asking us. How unusual would a difference of 0 be to observe? And then we have minus 0.04. And then we would divide this by 0.021. Okay, that's the answer that we got on the previous step for that square root. We don't have to do it again. So I'm not going to demonstrate this on the calculator this time because it's the same as the earlier problem that we did. So let me just go ahead and do it on my calculator and make sure you get the same thing. I get a z-score of 1.90. With these new sample sizes, would the difference of 0 be unusual? What do you guys think? So it is almost 2 standard deviations, so I would say it's pretty unusual. It's not completely unusual because usually we say that if it's above 2 standard deviations, it's unusual, but this is really close, right? So I'll say it is much more unusual now, since 1.90 is close to 2. Closer to 2, I should say. Okay, so let's keep going here. With these new sample sizes, what is the probability of observing a difference in sample proportions that is less than 0? So what is the probability of observing a difference in sample proportions that is less than 0? Okay. I think they meant greater than 0 here, okay? I think this is a typo, so I'm going to change it to greater than 0. So if we look at the distribution, here's what we have seen, right? Way over here now is a z-score of 1.90. And what we want is everything that's above that. So remember, this is going to be normal CDF. I've got 1.90 there. And I'm going to go until 1E99. Because I've done this so many times in this lesson on the calculator, I'm not going to demonstrate the calculator usage for you guys. So I'm going to do 1.90 as the lower limit, 1E99 as the upper limit, and I end up with 0.029. Okay, if I round it. Okay. So what conclusion would you make using alpha equal to 0.05? Well, it is significant. In other words, getting 0 or more is unusual. Okay. What conclusion would you make using alpha equal to 0.01? So I would say 0.05, it is significant, but 0.01 implies that it is not significant, right? Because 0.029 is smaller than 0.05, but it's also bigger than 0.01. So we need to be careful here. For 5% significance, it's different than for 1% significance. Now, I don't want you guys to lose sight of what happened here. What happened is that a difference of 0 was not that unusual in this picture, is it, right? 0 was not that unusual when you had small sample sizes. But as soon as we increased the sample sizes, it made those two pictures skinny enough now that 0 became an unusual value. And so that's why it became unusual, and getting high sample sizes is a good thing because it allows us to distinguish the two distributions and make sure that our difference in the end is accurate. Okay, guys, that is all for this lesson. I hope this video was helpful. Thank you very much for watching.